Okay, so it's 3 o'clock now, so we can get started. If someone could, close the door. People still running in. Okay, so thanks for coming to my talk on Qt Quick 3D in VR. And so, yeah, thanks. Let's just go ahead and get started. So here's a bit of an agenda of what I plan to talk about. Short introduction, and since we're talking about something very specific today, I need to drill down a bit and introduce a few different topics. And then I'll talk a bit about Qt Quick itself, what that is and what's special about it when it comes to VR. And then the actual rendering aspect, the technical details of rendering in VR, or at least to these head-mounted displays like this one. This is Oculus Quest 2. And the input methods, and then some additional fun with physics and collisions at the end. So let's get started with the introduction. So who am I? My name's Andy Nichols, and I work for the Qt company. I work on the graphics team in Oslo, Norway, so not too far from here. I've been working with Qt for about 15 years, but I've only been with, professionally with the Qt company and its predecessor companies for the last 13 years. And mainly been focused on embedded Linux. Well, originally embedded Linux and like the graphics on the embedded Linux, like so the embedded Linux port. Now I'm much more focused just graphics in general, so the actual renderer. So the 2D renderer for Qt Quick and now the 3D renderer for Qt Quick. I maintain those things and work on a team of people that are also developing out that further. And that's who I am. So glad to be here. So what's this talk about? I'm not here to sell you anything. I mean, Qt's awesome, but the thing I'm talking about doesn't exist as a product yet. It's something I'm actually developing currently. And it's more been a passion project up until now. Just something I'm doing for fun, and that's, actually something that we're interested in developing now as the Qt company. And so it's more of a chance for me to geek out and talk about like what the development looked like so far, talk a bit about API design, something that, we haven't had a VR API in Qt yet. And then some of the technical implementation details, like especially with regard to how do you actually render to a head-mounted display. So first off, how many of you know what Qt is? I think I need to ask that at this kind of conference. So almost all of you, so I won't spend too much time on that. I mean, Qt is a C++ application development framework. And I think Patricia said it well this morning that it contains so much, it's almost an OS at this point. It really is very broad in scope. So, and it's, not only C++, but also we have Python bindings, and then we also have a technology called Qt Quick, which I'll briefly talk about next. And we also have, an IDE called Qt Creator and lots of tooling around actually using the Qt and the Qt ecosystem. So, but we're actually here to talk about Qt Quick, which is a runtime on top of Qt that is a combination of a renderer and a JavaScript engine that's actually binding to the things in Qt to, instantiate the Q objects into a scene in a hierarchical declarative manner. So you can see here, this is a very brief example of QML code. You can see it's declarative. You have a window, it's a certain size, it has a name, and centered in this window is a button, and this is what you get. So again, under the hood, I mean, these are all C++ objects, but it's instantiated by this JSON-like syntax, which we call QML. So it's a mix of, say, Java, kind of like JavaScript object notation and JavaScript itself. So in addition to that, we have a renderer that actually will take that scene and render that using hardware accelerated APIs like OpenGL, DirectX, Vulkan, Metal, depending on which platform you're actually on. So, and now more recently, we've actually introduced additional 3D APIs for Qt Quick, which we call Qt Quick 3D. And this is a high-level 3D engine. That's kind of dark, but this is actually a scene that's was done with Qt Quick 3D. So rather than deal with the OpenGL primitives of buffers and textures and stuff like that, you're specifying models or materials to how to shade those models and lights and where the camera is and what you're rendering. So it's a high-level thing that us mere mortals can use to get to the same kind of things that are shown here. And it works very hand in hand with tooling. So you actually export a model from a 3D editor, and that will work in the 3D engine. And so really the short story is that it's adding 3D support to the Qt Quick runtime. Okay, and so one more thing to introduce, since we're talking about VR, and we want to render to the display headsets. There's another technology by the Kronos organization called OpenXR. And this is an API, a cross-platform API that lets you render to both VR and AR headsets. So it's I guess here it has a lot of examples of different companies that support this API. What the device I'm showing today is, like I said, the Oculus Quest 2. This is by Facebook. And Facebook is very pro OpenXR. I think all of their proprietary APIs they're moving them over to OpenXR. So that what's nice about that is that if you use that API, then it actually works on all the different headsets that support OpenXR. So that was the clear choice for me, not having to write something specific for the Oculus SDK, and that only works on Oculus, and then you couldn't use it with Vive headsets or whatever it may be. So that's just a bit of background there. Okay, so that's kind of all the technologies involved. Now I want to talk a bit about the intricacies of Qt Quick itself and some of the challenges that come with using Qt Quick as a technology for VR. So first off, I want to talk a bit about this transition between 2D and 3D. So by default, Qt Quick is a 2D UI framework, and Qt Quick 3D introduces the ability to have a viewport into a 3D scene. So in this case, the view 3D item is your viewport into the scene. It's a 2D item that contains a 3D scene or views a 3D scene. So in this case, it's just the children of the view 3D is the scene. So it has a directional light, a perspective camera, and a model, and that would just show you a sphere that's lit in 3D. So this is your transition from 2D into 3D, and that is, I guess, the first thing that you need to know. The other way around is that you have a 3D scene, and you want to show 2D content in the 3D scene. So bring 2D content into 3D spatial space. So there's a couple of options here. The first is actually putting the 2D content into a texture. And in this example, it shows that you have a texture item that's actually being used as the the base color map of this cube. And you can embed a 2D Qt Quick item as the texture. So in this case, it's just a button inside of a gray rectangle that gets mapped to every face of the cube, because that's how that works. And that's the most flexible option. But you also have the possibility of just directly projecting 2D items into the 3D scene instead of going through a texture. So in this case, I have a model, and then there's a button that's a child of that model, and then it's above the model here. And that's rendered directly into the scene using the 3D projection of that particular part of that spatial scene. And this is pretty useful, because if you want to put text into a scene and you want it to be very clear And with the correct projection, you could just anchor it to some 3D object into the scene. So that will be pretty useful in VR when I get to that. So the biggest challenge, though, when it comes to VR is that Qt Quick is very tied to the window, like there being a window, the Qt Quick window, because the whole rendering process is actually tied to, you have a window and this Qt Quick window, and every, if you case with a monitor that refreshes at 60 hertz, every, 16 milliseconds, you're going to have a V blank, and then it's going to say, okay, it's time to render. And then it's actually the window that's facilitating all of the rendering of the scene. So actually making sure that things are getting updated and that it's actually rendering at the right times. And so at least the way that Qt Quick's architected, like the window is everything. But in VR, like you don't necessarily have a window. Like you are, yes, in practice, you have 2 screens on the device, and each one of them is flat. And so you are technically projecting to something flat, but there's no window. Like you're directly in when you're stereoscopic rendering, if anything, you're already in 3D space. So the whole concept of window kind of breaks down if you have a head-mounted display. So how do you work around this with Qt Quick? Because by default, everything requires that you have a window in a scene. So we have this thing called Qt Quick Render Control, and this separates you, or this gives you the opportunity to actually hide the details of the Qt Quick window and actually give you the possibility of manually running all of the things that Qt Quick window would have done. So I just show a couple of examples here of how it would look. So you create a render control. You still create a Qt Quick window, but you don't. You make its parent the render control, so then it doesn't necessarily show it on the screen. Now you have an off-screen window that you can manually specify what are you rendering to, so what is your render target, how big is it, and then manually call, say, polish items, begin frame, sync, render, and end frame, which are the things that are necessary to actually render a Qt Quick scene. So this is very flexible because now you can render into any texture, you can render anywhere, you can render off screen, and Qt Quick just behaves like it is a window. So now what I wanted to do was, instead of that example where we had a window, I want to have a VR view that's actually, this is the view in the top level view for the scene. So this XR view, because we're using OpenXR, so I call it XR view, and this would replace the view 3D and the window. So the way it works is it's also the scene itself. So it's the view, the window, and the scene all at the same time. It creates a render control that renders to an off-screen surface and does all of the OpenXR magic that you need to do to actually use OpenXR. So actually instantiating the headset and setting all the formats, and it handles all the details for you. All you have to do is instantiate the XR view instead of a window. And yeah, it also handles the input, but I'll talk a bit about that later. And the other thing is, like you have a view and then you have an actor. So this is the actual, since you're already in a 3D scene, the actor is the location of the headset. So wherever the actor is in the scene, that's going to be the base set for the headset. Everything else is an offset from that. So, and this is what it looks like what the API looks like and what you would see in the headset with such a thing. So again, the XR view, you have a scene environment that says basically render the background black. You have the actor 1 meter off the ground and 1 meter back. 100 is in centimeters in this case. And just a light and a crab. And so just me trying to be still in the headset. But it's pretty simple to actually get something working. So like with just that few lines of code, you can have something running in the headset showing a model. Okay, so that's kind of the preview of the API. The actual details of the rendering is that you have with the HMD, it depends on the headset, but for the most part, this is what it looks like. You have the headset, and there are two screens in the headset. Sometimes there's one screen, and it's just splitting it, but in this case, it looks logically like two screens, and each one of these screens has its own swap chain. And so what that looks like in practice is just like a triple buffer of 3 textures of this 1440 by 1584. And so with OpenXR, I can create these and say, okay, I want them to be RGB8, sRGB. This is the maximum size. You set up all that stuff, and you basically have these 2 swap chains. And then you need to render to both of those to get the stereoscopic view. You have a bit of options, at least with this headset. You can set like what frame rate you want. By default, it's 72 FPS, which is already pretty tight because now I think it's like what, 7 milliseconds, and you have to do it twice per frame because you're having to render the scene twice. And then the only other detail is that each of the cameras, like there'll be 2 cameras, one for each eye that actually shows up in the scene, and each one will have a slightly different projection matrix that you need to render the scene from. So this is a bit what the rendering process looks like from the OpenXR side and the Qt side, is that we just begin the frame, we ask XR to give us the updated pose positions, like so where is the headset relative to the starting point, where are the controllers, like what is the eye position, because some of the headsets you can actually change the distance of the eye, so that'll actually change between scenes. And so you get the different poses and projections for the headset. And then you would update the actual objects in the scene that reflect those things. So like for the XR actor, you'd change the position that it's at, or the hand controllers, if you had hand controllers, you'd change the offsets that they're actually at in the Qt Quick scene, and we would do that for you. And then you need to render the left and right eye. So what we do is we set the active camera, because we have 2 cameras in the scene, and with View 3D, you can say, or in the XR thing, it would be, you set the left camera as the active camera, so now you're going to be rendering from that camera's perspective. You want to set the render target to the current swap chain for that eye. So you ask XR, oh, for the left eye, what's the current swap chain or the current buffer in the swap chain? And you set that as your render target, and then you render the scene. And then in that same frame, you do the same thing for the right eye. So you just set the camera, render the scene, or set the current render target to that buffer, and then you render the scene, and then you're done. So you've actually rendered the scene twice from two different perspectives, and that gives you your stereoscopic view into the headset. What that looks like, well, it depends, because Qt Quick supports different backends, and so does OpenXR. So in this case, right now we're supporting OpenGL, OpenGL-ES, Vulkan, Direct3D, not Metal. I don't know, at least none of my hardware I know of works on Metal. I haven't actually tried, but I haven't wrote the backend for Metal either. But it does work with Qt Quick in the RHI, so Qt can render to Metal, but I don't have any special XR code for doing that. But I have this interface for all of the different paths that could require some special setup, like how do you get the render texture, for example. I guess I could go over for Vulkan. There's a couple of quirks that you have to go through if you're using Vulkan with OpenXR. Normally Qt Quick would set up your Vulkan instance and your Vulkan physical device itself because it controls everything. Well, in the OpenXR world, it's the headset that's responsible for all that stuff. So you actually have to tell OpenXR, what extensions do I need to render to this headset? So you have to query that first, and then also get the physical device to tell that. And then you have to tell Qt as well, because Qt's going to do all the rendering. So both of them need to do rendering. So Qt's actually pretty flexible in this regard of being able to delay saying oh yeah, here's the Vulkan instance now that I have it. So And you can see here, like just a quick code example of like how you can just set on the QQuick window the graphics device and the configuration in the Vulkan instance. So it is possible to do that. And yes, so the render target itself for Vulkan, again, you're asking the swap chain, what's the current buffer? It's going to return this XR swap chain image Vulkan KHR texture pointer, and then you have to cast that to a VK image that you can use in QQuick. And you just getting this QQuick render target. We have a convenience method for turning a Vulkan texture into a render target for QQuick, because again, QQuick can render to Vulkan textures, or it's very flexible. So just rendering, in this case, rendering directly to the buffer given by the headset. So, and that brings me to the next point, which is performance considerations. Performance is like super important with VR, because if you're not hitting your like the optimal frame rate for the headset, like you'll make your user sick, either whether you're being really late with giving the buffers to the headset, or you're not rendering at 72, 60, 90, 120, whatever's required for the particular application. If you're not actually hitting those marks, like that's your user getting sick and taking the headset off and not using your software. So in this case, I guess with this particular headset, because this is actually running Android, so it's basically a mobile phone with a screen inside of a headset. So you have to treat it like an embedded device or a mobile device. And the thing about these devices is that like they're using tiled renderers, and like FBOs are super expensive. So what you want to do is actually render directly to the screen itself, like skip any of these off-screen surface things, which actually is possible with QQuick by either rendering as an overlay or an underlay. And in the toolkit by default, I'm going to do underlays for the VR module, but it also means you can't use post-processing effects, which they don't work that great in VR anyway. Or a lot of the tricks you do in post-processing effects don't work as a stereoscopic effect. But it's also like for headsets like this, it really kills performance to the point where you're never going to hit your frame time budget. And actually, a lot of the tricks that are done by these headsets require that you're running directly onto the screen buffer, because like it's not directly on the window. They have their own compositor that they're doing kind of tricks where like the inside of the image has higher resolution than the outside of the image. They're doing all kinds of crazy stuff. So you actually have to render directly to the screen buffer for those things to work, because if you render to an FBO first and then copy it to the screen, apparently it doesn't work. I don't know what they do, but I tried it, and not only does it not look as good, but it runs about half the speed. So important thing is to render directly to the screen buffer. The other thing is that normally tone mapping is done as a post-processing effect, but at least in QQuick 3D, because of how we're already rendering for embedded in mobile devices, we already have the option. If you're direct rendering, we do the tone mapping as part of just the draw call when you're doing your material, so it's not that big of a concern. Second thing is that, it's actually for the same reason. When we're doing forward rendering, because deferred rendering requires lots of intermediate buffers, which are using FBOs, which are really slow. Problem is that you can't do as cool lighting effects, but again, your mobile hardware, or even on the desktop, like you really want to save performance. So it's best to keep this forward rendering in mind, and QQuick 3D is using forward rendering by default. And the last thing is actually, just like all rendering, draw calls are your enemy. You want to reduce the amount of draw calls down as much as possible. And at least with the approach that I took, and you could see in the previous description, was that I'm actually rendering the scene twice, like the whole scene twice, one for each eye. That in itself is also not ideal, because no matter what you put in the scene, you always have 2 draw calls. And it is actually possible to make this one draw call by doing, there's some extensions both in OpenGL and Vulkan where you can bind 2 output buffers and then use instance draw calls to change the projection matrix of each one, so that there would only be 1 draw call, but then the 2 render targets. But I'm not doing that yet. It was a bit involved, and required some vendor-specific extensions, at least in OpenGL, so something I'll have to do a bit more experimenting with, but at least right now, you can see in RenderDoc, it's for just that crab, it's 2 draw calls, so just 1 for each of the screen buffers. Also, side point, if you're actually using the Oculus SDK, they have their own version of RenderDoc that works really well with that headset, so I can recommend if you're doing VR development, like despite the Facebook association, the Oculus stuff is actually pretty good development-wise. Okay, so that's just rendering to the headset. The actual input, another big part of these guys. I got them backwards. So usually with VR things, you have these hand controllers, and these what you see in the headset is when you're collecting the pose, you're getting the offset from the head. So if you think about the scene, this is the 2 right and left hands is just going to be a rotation and position relative to where the actor's head is. So if you look in this example, this is where I've added 1 controller to the scene. So we'll play a video. And so I have a flashlight, and you can do the Doom 3 style, like everything's dark and I'm lighting it up with my flashlight. And it looks really good in the headset. Like it's kind of scary to be looking in the dark at that funky looking crab. But you can see here that, again, you have the actor, and the controller is a child of the actor that automatically gets you your position offset. And what we'll do is we'll, in the back end, look for the item, the XR controller that for each the left and right, depending on which controller you set it as and which pose you have, and we'll set the correct transforms for that item so that whatever you may have in the scene as a child of that item, it'll actually get updated. So in this case, I have this Lentera item that's the flashlight that is moving that object around in the scene. So you have the model there, and then the model has a light attached to the front of it so that it's actually doing the spotlight. So that explains that code in that example. The second thing is that, that was just moving an object around. The other thing is that you want to point at stuff. So want to point things out. So like in this case, if you've ever done the VR thing, you want to point where you're going and then teleport to that. So I have this, pointing in this little ball on the ground that says where it's at. So we have what you call picking API. So it casts a ray into the scene, sees if it intersects with any objects, and then it returns the result of what object was it, how far away was it, what position was it at, what was the normal at that. And you can use that data to actually figure out where in the scene is that? Is that something I should care about? So specifically for this example that is here, I'm just saying, am I intersecting with the floor? Because now I want to know where on the floor should you teleport to if you were going to implement teleporting. So that's all things that we already had in Qt Quick 3D. I just take advantage of in my examples. The other thing is that you want to combine 2D and 3D in VR, which means that maybe you want to, most Qt UIs are designed for either touch or mouse. So if you just draw the little line with this thing, that's kind of like a mouse. So I added an additional helper class called this XR virtual mouse, and that will just do all of the translation for you if you have this in your scene, and you can just assign which buttons or which clicks on the mice. And so that makes it possible to, have a UI there that you could scroll, or in this case, I'm just drawing a little circle to show that, it works pretty well, the actual feedback, so I can get very quickly based on where the arrow is, what part of the scene, because that's just a Q quick item that has a mouse area in it, and I'm just drawing a red circle and a label where that is in the scene. And last thing is keyboard input that sometimes you need to actually input names and stuff into user interfaces, and so you can actually use Qt Virtual Keyboard as the keyboard input. Unfortunately, I got this working, but the input method itself doesn't work. So at least I've been playing around with this because input methods in Qt require that you have a window, and I have no window. So, or at least there's no window to focus. If like think about that, like if you're on an OS and you alt tab into something to get like input focus, you can't do that if there's no window to focus on. So it's something I have to think about because that creates a lot of problems. Okay, and so pretty quickly I can go through this last thing, which is physics and collision. So when I was working on this stuff, I didn't really think I needed it, but once you start like making demos, like you really see that collisions are really important. Like things like floors and walls, like so you're moving your character around and like all of a sudden you've clipped through a wall, and it's very unsettling when you're looking into a scene and there's a wall bisecting your face and you can see both sides of the wall. It's things you wouldn't think about. It's very unsettling. So I wanted collisions, and of course, if you think about like if you've ever played VR demos, like physics makes things fun, like being able to grab things and throw them. Like so, it's like I want to do a demo that does that. So I decided to integrate Bullet 3D as well. It was a separate module than the VR thing, so you could use it separately. But I said, okay, well, this will work good for VR. So I actually did a module that used Bullet 3D, which is it's a dynamics and physics library. It's done in C and C++. It's liberal open source licensing, a zlib library, so that made it convenient, as well as had CMake build system support, so it was really easy to include into the project, so as a third-party dependency without having to write lots of crazy stuff. So I created a small API Bullet 3D does a lot of things, so I wanted to really limit the scope down to, the bare minimum of what I needed for collisions. So I had like static bodies, which is things that don't move, rigid bodies, things that did move, and then collision areas like just invisible shapes that when you enter them, I get notifications. Which also means that I needed shapes because you have all these bodies, you need to actually define like some efficient shapes that aren't just the models themselves, because the thing that makes picking the ray casting thing so expensive is that it actually does triangle picking before it's all said and done to give you that normal reflection. So you want to make your collisions a lot simpler, so you can specify things like spheres and boxes and cones and planes, and it's possible, but also this collision shape property is an array, so you can actually compose them together. So something like if you're making a collision volume for a door, you have a box, and then you have a couple of spheres or another box for the doorknob. So you want to compose those shapes together. And then you have things like physics material, which is like, what is the bounce? What is the friction of the object? And then the overall dynamics world, because again, all these items exist in the spatial scene graph, like in this like 3D space, but they're not rendered. So you have a separate like entity that's actually keeping up with, the physics world. So in addition to the rendering, you also have this physics world that's running every frame or twice every frame that's actually saying, okay, what are the dynamics? And then resyncing with the scene graph of where these items will be after the dynamics engine has actually run. So, and this is what that looks like. I just like throwing some globes around into the scene. And also you can see a little bit in the bottom, like these are actually like some debug volumes. They're actually showing like the sphere itself of like what the actual volume is. So I have like a wireframe drawer that's actually showing you what it is, but you can turn those on and off. And so, that's about it. I've had a lot of fun playing around with this, and at this point it needs more refinement, and hopefully we'll be able to release these things as part of the Qt project soon. Because right now it's mostly been just me playing around in my free time, because I work on Qt Quick 3D, and while it's really cool that it's a real-time 3D engine, it's also it's like a game engine. It's fun to play with. There's a lot of things that you can do with it. So, and you do them with QML, so it's like really just fun to play with. So I end up doing these crazy things like this, and but I see it as something that would actually be useful, because again, we're not Qt, we're not focused on games and stuff, and like all these like VR frameworks, it's all game engines and stuff. And so really want to see like how we can, create good user interface tools for VR, since, that's our bread and butter really with Qt. So that's pretty much it. So yeah, thanks. And if you have any questions, please feel free to ask. No? Okay, well, you can ask me afterwards as well if you feel like it. But yes, thank you.